Chemistry 3202 course overview, Unit 1, Section 1, Lesson 3, Factors Affecting Reaction Rates. In these two pictures here, we have the exact same chemical reaction happening. This is the chemical reaction of iron being oxidized to produce rust or iron oxide. So it's the oxidation or rusting of iron. In one picture, we see a rapid, very explosive chemical reaction happening, and in the other picture we see a very slow, long drawn out process in which this automobile looks like it's been there for eons and it still hasn't completely chemically reacted or rusted away. So why the difference in these two rates of chemical reactions if it's the exact same chemical reaction that's happening? Why is one fast? Why is one slow? For further reading on this, make sure you go check your textbook, 466, 467, and there's a few extra nice little practice problems here you can try. You don't have to do them all. Okay, chemical reactions, therefore, we see from these diagrams proceed at different rates. And there are 5 or 6 factors that affect the rate of a chemical reaction, how we can speed up a chemical reaction or how we can slow them down. And these factors would include the surface area of the solid, the concentration or pressure of a reactant, the temperature of the reaction vessel or the reaction container, or the reactant, sorry, and number 4, the nature of reactants, you know, what are we mixing together, what types of compounds, and number 5, whether or not there is a catalyst present. And any change of one or more of these, it doesn't have to be all 5, any one of these changes could affect the rate of a chemical reaction, either speed it up or slow it down accordingly. So any one of these 5 could do that. The general idea behind this, again, we're still on that collision theory business. We're saying that in order for us to have a successful collision, we require collision, number 1. Particles must collide, remember? Okay, they must collide with correct orientation. Just a quick overview here. And number 3, sufficient energy. Okay, so we're saying then that anything that could possibly increase the frequency or the number of collisions, anything that would cause the molecules to bang together more often, then chances are we're going to get a successful reaction. Or anything that causes the collisions to be more intense. So if we can make them bang together with a lot more energy, then we're probably going to get over that activation energy barrier. Remember that threshold energy we talked about? Getting over that kick. So anything that collides much harder, much more energetically, chances are they're going to be able to, you know, there's going to be a quicker chemical reaction. So anything that would increase the number of collisions or the intensity of collisions will speed up the chemical reaction. Now the opposite of this will be true as well, because if we can make fewer collisions, that means we're going to decrease our likelihood that a reaction will happen. Or if we decrease the energy by cooling them down, then chances are if they do collide, they're not going to have enough energy, so nothing's going to happen. So anything that we can slow them down or reduce their energy will slow down the chemical reaction. So the opposite is true here. So whatever we talk about here, by speeding it up, if we do the opposite of that effect, then that's going to have the effect of slowing it down. So let's have a look at the factors that affect reaction rate. The very first one is surface area. Now you guys have experimented with surface area. Surface area is the amount of exposed material. You know, looking at a bowl of sugar, sometimes if the sugar is really fresh, it's nice and dry and it's real crumbly and there's real little tiny pieces of sugar. If the sugar is very old and there's a lot of water and moisture in it and whatnot, the sugar gets real clumpy and stuck together. The fresh, dry sugar is the one that has the greatest surface area because it has smallest particles. All right, so we're referring to the exposed matter. And in this sense, we're looking at the idea of, say, a chunk of wood. When we're lighting a fire, we like to chop the wood up into little tiny pieces called splits or kindling. And in that case, the splits or kindling would get the fire going quicker. Once we get the fire going, we put larger pieces on. So the splits or kindling would be the one with the highest surface area. Okay, and we're also looking at things like charcoal barbecues and whatnot. If you have charcoal barbecues, you like to put on nice, great big briquettes. It takes a long time to get them going, but they last a long time. If the briquettes are broken up to fine powder, doesn't last very long. It burns out really quickly. So there's a give and take here, isn't it? If we chop up all our firewood into little tiny pieces, we get lots of heat really, really fast, but it doesn't last very long. It burns real quickly, but it goes in one great big kaboom. Or if we don't cut up our wood and we keep the wood really big, then it burns much more slowly, but we don't get the energy out as fast. All right, so there's a trade-off here in surface area. A little explanation of what's going on with surface area. We can look at, say, an object, like this would be a piece of coal or something. So if we took a piece of coal that was 10 centimeters by 10 centimeters by 10 centimeters, that's a big hunk of coal, would fit in the palm of your hand. If we wanted to calculate the surface area, the amount of exposed surface here, we'd simply say surface area is length times width times the number of sides. So in this case, it's 10 by 10, and there's 6 sides. So this would have a surface area of 600 units squared. If we took that same piece of coal and started cutting it up into 1 centimeter cubes, we started cutting up into little tiny cubes like that, we could get 10 cubes this way, 10 cubes that way, and 10 cubes that way. And every single one of these cubes now would be exposed. In this case over here, all the stuff in the middle is not exposed, but over here we're getting at that. We're breaking this up into little tiny pieces. And if we calculate the surface area of this when we break it up, we've got 10 times 10 times 10, so 10 across, 10 up, and 10 back. That would be 1,000 little tiny cubes in that junk. And each little tiny cube would have 6 sides, and each side would be 1 by 1. So by cutting it up into little tiny pieces, I've made my surface area go up by 10 times. It's 6,000 units of surface area here now. So I've more than 10 times the surface area by cutting it up into little tiny pieces. Okay, so the significance of this then is that if we have one great big chunk of this stuff, if this is a reaction of, say, oxygen, it's supposed to be oxygen there, oxygen with our coal, the oxygen can only collide with the outside surface. And therefore, even though we have lots and lots of coal here, carbon, even though we have lots of it there, the oxygen is not colliding with the inner ones. Therefore, the only ones that could potentially react are the ones on the surface, hence surface area. Now, if we chop this up into little tiny chunks and start crushing it up, what we notice is that as we start crushing this, the oxygen now can start fitting in between the spaces of these little tiny particles of carbon. And what's happening here now is this part of the carbon was never exposed before because it was trapped in here. Now it's exposed to the oxygen, so we're getting collisions here and all over the place that we didn't get before. So by having smaller pieces, we're getting more collisions. And remember what we said. Anything that increases the number of collisions would increase the likelihood that a faster reaction would occur. There we go. Okay, so I'm not sure what I got done here. The oxygen, okay, this is a reaction of hydrogen and metal. Okay, so acid and metal. So in this case, the hydrogen ions would be able to get in and amongst the metal and therefore speed up the reaction. Same thing if it was oxygen and carbon. Same sort of thing happening. All right, so our generalization would be here then that if we increase the surface area, if we cut it up into little tiny pieces, we should increase the rate of reaction. And we would want to state that according to the collision theory. So what would the collision theory say about this? They would say the greater the chance of collisions, the greater the chance the reaction would occur. And if we have increased surface area, we're going to have more molecules that are now available to collide, and therefore more collisions means we've increased the frequency of collisions, we've increased the rate of the reaction. And the idea behind this, I guess, is if you're on a busy highway, very, very busy highway in a big city somewhere, you get a lot more accidents happening because there's more chances of collision because it's just so busy. There's cars going all over the place. As opposed to a place out around the rural area in the country where there's less cars around, you got the road to yourself and you don't have to worry about colliding with someone. So that's sort of what's going on there. Okay, so the greater the surface area, the more particles you have that are zinging around and going to be able to collide. Some practical examples here of this would be things like grain elevators, coal mines, and say fuel injectors in your car. The purpose of a fuel injector or a carburetor in your skidoo or your car or your chainsaw is to take the liquid gasoline and spray it out into a fine mist to make the gasoline particles as fine and as small as they can so that they can mix more with the oxygen. The more mixing you get with oxygen, the more efficient the car or the skidoo is going to be. And that's what the purpose of the carburetor is, to mix the air and the gasoline. Okay, here's a fellow in a gold mine. He's chipping away at the gold, but not at gold, coal. He's in a coal mine. He's chipping away at the coal, and in the process he's stirring up a lot of coal dust. And if he should happen to have some static discharge here, static electricity, or sit down for a cigarette or something, which they're not allowed to do, that ignition spark could be enough to ignite all this oxygen now that's mixing with the coal dust. So we risk explosion because of all this very fine powder of coal that's floating around in the air. And the way they get rid of this is they wet it down. All right, they would have water spraying in here, and the water would wet down the dust so that it takes it out of the air. All right. Same thing's true with grain elevators, like wheat and whatnot. All the wheat dust, very explosive, and that would catch on fire and explode. So therefore, you're not allowed to smoke and whatnot around grain elevators because there's a big risk of explosion. Okay, the next thing we're looking at is the concentration of reactants, and we're saying, again, from a collision theory perspective, anything that's going to cause more collisions should cause a faster reaction. So if we're going to increase the concentration of a solution, we're going to make more atoms, more molecules there that are going to be able to collide because it just means there's more there. It's a greater concentration. All right. Now this is only true for gases and aqueous solutions, where we have the concentration given in moles per liter. If we had a pure solid substance or a pure liquid substance, so for instance, could we increase the concentration of a chunk of zinc? Well, we could increase the surface area. We could cut it up into little tiny small pieces, but are we increasing the amount of the zinc? Absolutely not. We still have the same amount of zinc. It's just that now it's in a finer form. So there's no way we could increase the concentration of a pure solid. We still have the same amount, so we have the same number of moles of zinc. Okay, so no effect there because of concentration for solids. And if we look at an example of this, we're saying, okay, here's going to be a piece of zinc, same size zinc. We're going to drop one piece of zinc in the same amount of 1 molar hydrochloric acid, and we're going to drop another piece of zinc in 6 molar hydrochloric acid. So the hydrochloric acid is the variable that's changing here. So what would be the effects? Well, right here, we're saying that in the 6 molar hydrochloric acid, there's 6 times as many moles of HCl. So therefore, theoretically speaking, we should get 6 times more collisions. So therefore, the reaction rate should be 6 times faster, depending, right? But it's going to be a lot faster. We don't know if it's going to be 6 times faster, but it's going to be a lot faster because there's 6 times more molecules to collide. All right? Now we can increase the concentration of hydrochloric acid 2 ways. We could add more HCl to the water, or we could let the water evaporate. So if we left the cover off the hydrochloric acid container, the water would evaporate and it would get stronger. All right? Same thing is true here. We can make the HCl weaker by adding water. Okay? We could add water to this, or we could remove some of the hydrochloric acid, making it a weaker solution. We could dilute it by adding water. All right, so there's certain things we can do there. So we can also look at gas pressure here as well and say, okay, well, what's the effect of increasing the pressure on a gas? And we can do this by using a flexible piston here. So here we got 2 gases that are capable, they're colliding with one another, but nothing's really happening here because there's a lot of empty space and these guys are free to move around. But what would happen if I would push down on the piston? If I push down on the piston, what I'm doing is I'm cramming all these gases in a smaller confined space. And what's going to happen is they're going to start colliding with one another more and more and more. The more I cram them down, the less space there is. So we're going to get more and more collisions. So in a sense, I've decreased the volume of my container, so therefore I increase the concentration here. The concentration on this side is greater than it would be here, right? There's less empty space. So in terms of gas pressure, Increasing the pressure of the gas is exactly the same as increasing the concentration. You have more gas molecules, therefore you have more collisions. Okay, under high pressure or higher concentration, the gas molecules are going to collide more frequently, and therefore we should see a faster rate of reaction. More collisions, faster rate. The opposite is true here. If I should pull out on this piston, I'll pull out on this and I suck all this gas out. What I'm doing is I'm drawing it out into a larger container, and now there's lots of empty space here, so these guys don't have to collide as much as they did over here. So by pulling them out, we're going to have a slow reaction here, and over here we're going to have a fast reaction. So this will be slow, this will be fast, and the reason this guy's fast is there's more collisions. There we go. And the reason that guy is slow is because there's fewer collisions. And the idea being, of course, if we have a traffic highway here, and we got traffic now that's coming on 2 lanes, and they're going to diverge into 1 lane, where do you think most of the accidents are going to happen? The accidents are mostly going to happen where the traffic starts coming down into 2 lanes, right? Because these guys are trying to compete for the same space, so that's where we're going to get the collisions, because now they're going to be crammed together, right? And that's what's happening with the gases. We're cramming them together here, so we're causing them to have less space, and therefore they're going to collide more frequently. This reaction is going to be much faster. That's what happens in your engine. That's why when the piston moves up in your engine, it compresses all the gas, causes an enormous pressure, and by doing so we get a lot more explosion. The car is more efficient, and we get a lot more power because the gases are being compressed together in your car engine. Okay, if you had a leaky seal here on your car engine, the pressure would escape, and then the explosion wouldn't be as violent and as powerful because the pressure would be reduced, right? So good job, good idea to keep your car up to date. Okay, temperature. Temperature, remember from a previous lesson, temperature is proportional to the average kinetic energy of the particles. And that's how we measure it with temperature. So if we're saying that temperature is a measure of the average kinetic energy, then technically speaking, if we doubled the temperature, then that has an effect of somewhat increasing or substantially increasing the kinetic energy. So the molecules are going to be moving much more quickly at a higher temperature. And if they're moving more quickly at a higher temperature, they're going to collide more often because they're moving faster, right? People who speed in their cars are at a greater chance of having an accident because they need more room to maneuver. They need a bigger highway. They need more room to take turns because you're going so fast. So if particles are moving more quickly, they're going to collide more frequently. Not only that, if there is a collision, because they're at a higher energy, they're going to collide with greater intensity. All right, so 2 reasons happening here: more collisions and more intense collisions. And we see a little diagram here. Of course, with this fire, these molecules now are starting to zing around much more quickly, more intense, and if these guys should happen to collide, they're going to collide with greater energy. All right? Now, the problem with temperature is saying just because we warm something up doesn't necessarily mean the chemical reaction is going to occur faster. It's okay if the chemical reaction is happening, but if the chemical reaction is not going, then just by increasing the temperature doesn't necessarily mean you're going to start the chemical reaction. Let me show you a graph. You guys have seen this before too. Here's your threshold energy, remember? If not enough molecules have reached this threshold, so for instance, if we're at a temperature that's really, really, really low, let me just do this one in green for you. If we're at a really low temperature in green, no molecules have reached the threshold energy. All these molecules in the green temperature are all going too slow and too cold. Even if I do increase the temperature a little bit and go up a little bit, I still don't have enough molecules that are going to be there. So it depends on what temperature we're at and what that threshold energy is. Okay? So what they're getting at is if we increase the temperature, we're going to cause the graph to shift to the right. So this 20-degree graph, the average of 20 right here, most of the molecules are around 20 degrees. If we increase the temperature to 30, the graph flattens out and moves to the right, indicating that more molecules now are going to push to this side of the, more molecules are now at the high energy point. So by increasing the temperature now, we've increased the number of molecules that could potentially collide. And that's a good thing, because once they start colliding and start producing a successful chemical reaction, now more and more and more molecules have that potential here to do something. So two factors here. We increase the number of collisions, and by shifting the curve to the right, it causes more molecules now to be beyond that threshold energy. And we can see that here with an activation energy diagram with the potential energy. If we're way down here, if the highest energy we get is here, then there's no way we're going to get a chemical reaction. The molecules have to get over this activation energy. So by increasing the temperature, it causes more molecules to get enough energy to get over that bump. So that's what we're looking at here. Now, a greater number of molecules at 30 degrees are now able to get over that threshold energy, or the activation energy. And that's a good thing if you want the reaction to speed up. If you want the reaction to slow down, then you might want to cool it down. Right? By cooling it down, it causes the graph to slide down, and therefore we would have a colder graph. So for instance, if I wanted my yogurt not to spoil, I would put it in the fridge at about 4 degrees Celsius. And if I put my yogurt in the fridge at about 4 degrees Celsius, I'm going to get a curve that's way down here, and that's a good thing, because if my bacteria in my yogurt was at a very high temperature, the chemical reactions for spoilage would be increased, and the yogurt would go bad, or the milk would go bad very, very quickly. But by putting it in the fridge, the chemical reaction will not occur for spoilage, because the chemicals that do spoil won't be at that high energy. They won't be at that threshold. Okay, so what we're saying then, at the lower temperatures, only a few molecules have sufficient energy to overcome the activation energy. As we increase the temperature, more and more molecules now have that minimum energy, and therefore it's more likely that a chemical reaction occurs. So a dual effect there, two effects of temperature. The next thing we're talking about here is nature of reactants, and this refers to the nature of what we're mixing together. What state they're at, whether they're solid, liquid, or gas. What types of bonds are happening, whether it's ionic, covalent, network covalent. It depends on what type of structures are going on there and what's happening. So that's the nature of the chemical reactions. So what it is we're mixing together. So one of the things we can look at here is the state of matter, solid, liquid, gas, whether it's aqueous, the size, the shape, the strength of the bonds, and all that stuff. So what we're going to do is make generalizations only. All right. So there's always going to be exceptions to the rule here, but we're going to make some broad generalizations that will help you give you an idea of what you're thinking about when you're looking at the nature of chemical reactions. The very first thing we want to look at is states of matter. Gases tend to react faster than solids or liquids, and the idea behind that is that gases, remember the kinetic molecular theory? They diffuse to fill their container. So if gases are going to fill their containers, that means they're going to mix really, really well, and if they mix really well, that means we're going to get more contact, more collisions. And that's a good thing if you want a fast reaction. So that's why gases tend to be faster than solids and liquids, because gases mix evenly. Aqueous ions tend to react faster than species in other states of matter. And the reason behind that, well, here's a little example. The reaction of, say, methane, which is a gas, reacting with oxygen, which is another gas, these guys will mix completely, and that's a very fast chemical reaction. That's going to go kaboom, right? If we take the exact same combustion reaction, but this time we use candle wax, C25H52, this guy's a solid. In order for this candle wax to ignite and burn, it first must melt and then vaporize. And the only place that the candle is hot enough to melt and vaporize is right at the base of that flame. So because of that, we have minimal contact between the oxygen and the candle wax, and the candle wax has to be in the vapor form in order to ignite and combust. So because of that, this is going to be a very slow chemical reaction because of the states of matter. All right, so that's an example for that. The bond type, all right, what type of compounds are mixed together? Covalent bonds tend to be the strongest bonds of all types. So it takes a lot of energy to pull apart covalently bonded atoms. That carbon and oxygen there is held together very, very strongly with the covalent bonds. So in order to pull that apart, it's going to take a lot of energy, and that reaction would be relatively slow. This reaction here involves some simple ions, a few complex ions, but nonetheless it's going to be very, very quick because these guys are all aqueous solutions. And as soon as I mix these three reactants together, they mix completely, and we get lots of collisions and lots of mixing, and therefore anytime we have lots of collisions and lots of mixing, you're going to get more collisions and hence a better chance that a reaction is going to occur. So relatively speaking, this reaction is going to be a lot faster than that reaction because of the type of compounds we're mixing together. Okay, so that's state of matter bonds. The next thing is bond strength. And this is a situation where we want to look at the strength of the bonds that are involved here. Now this is going to be Unit 3 stuff, where we can look at the different types of bonds that are going on, and we know the energy, so we can tell which ones are easier or harder to break. So that's what we're talking about. But generally speaking here, this chemical reaction here, C2H6, is pretty fast. That's the burning of ethane. This guy here, the burning of ethine or acetylene, ethane and ethene, this one's much, much faster than that one. And the idea being is that the double bond is more chemically reactive and easier to break than the single bond. Triple bonds are even faster again. So the nature of the bond and how strong these bonds we're looking at here and the number of bonds is all going to be determining how fast the reaction is going. So the easier the bonds, the easier it is to break. That means there's less energy needed. The harder the bonds are to break, that means there's more energy required. We have to get it hotter in order to get it to go. Here's another one, the number of bonds. Okay, the number and type of bonds, that should be self-explanatory. If we look at, say, the combustion of methane versus the combustion of kerosene, methane, I only have to break 4 CH bonds. That's easy. Look at the kerosene. Look at all the bonds I have to break here. All these CH bonds, all these carbon-carbon bonds. You start adding up all the bonds you have to break here, it's quite substantial compared to this. So it makes no wonder that this would be slower and the other one would be faster. All right, because it depends on the number of bonds that have to be broken. And last but not least here, the catalyst, the effect of a catalyst. Now, catalysts are these wonderful things that we can add to certain chemical reactions that actually speed up the chemical reaction. It's like, poop, put it in and there you go. A reaction that was doing nothing, all of a sudden you drop in a catalyst and the thing just goes nuts. Okay, so this is a species then, by definition, that speeds up a chemical reaction without being chemically changed itself. So it's pretty neat. You can drop it in the container, the reaction speeds up, and once the reaction's finished, you take your catalyst out again so you can use it again. Wicked. All right? So we're looking at some examples of catalysts, and some common ones that we see around us every day would be, well, it's not so much common, I guess, every day, but the decomposition of peroxide. H2O2, very slow to break down. H2O2 breaking down to oxygen and water really doesn't want to do it that much. As soon as you drop in some MnO2, the thing just bubbles up and goes crazy uncontrollably fast, and that catalyst there, the manganese, you can use it again after and after. You can recover it. The production of ammonia from nitrogen and hydrogen. Nitrogen is in the air we breathe. It's not very chemically reactive. It doesn't want to do anything. When it mixes with hydrogen, it still doesn't want to do anything. But as soon as you add an iron catalyst, look out. It goes crazy to produce NH3. So what's up with that? There's also catalytic converters in your car, all right, in the muffler system, and the catalytic converters convert NO, nitrogen monoxide and carbon monoxide, to produce nitrogen and carbon dioxide, less harmful gases, and that's the platinum catalyst. And you know that without that platinum in your muffler system, this reaction would never happen. Okay, and that's the production of ground level ozone that prevents. So without the platinum catalyst, the ground level ozone would be a problem here. But with it, it's not, because this reaction can occur. So catalysts are pretty neat in the fact that they speed up chemical reactions. Okay? Now, we got to look at the catalyst and say, well, what's going on here? We're saying that okay, so the reactions have to collide with sufficient energy to get going, and we know there's an energy barrier to a chemical reaction. So the way the catalyst works is that if we could somehow, we want the exact same chemical reaction to happen. We don't want anything to change. So if we could somehow lower the energy barrier, so that's what the catalyst does. It's going to provide an alternate energy pathway for the reaction to proceed, and it's a lower energy pathway. So if this is the reaction normally, that really it's hard to get going because you have to give it a great big kick. As soon as I drop in the catalyst, I lower that mountain. I lower the energy barrier somehow. It goes through a different pathway. Instead of going over the hill, it's like it's going through the hill somewhere. It's like there's a magical tunnel there somewhere that provides less energy, or there's a lower energy pathway. So what happens is the reactants come up here and say, hey, I can take the long way around, which is going to take a lot of energy, or, oh, look at that. A new portal's just opened up. I'm going to take the easy route. And, of course, every single one of these reactants is going to take the easy route, and that's going to speed up the chemical reaction. So the catalyst has lowered the minimum required energy that's needed for the reaction to occur. And if we can lower the amount of energy, then obviously the more molecules now are going to have successful collisions. Okay? And the reactants and products are the same in every case. It's simply saying the catalyst, all the catalyst is doing is providing a new lower energy pathway. There we go.